Okay, in this one we have a hose, and it's putting out water of 1 liter per second, and it narrows from a radius of 2 centimeters to a radius of 1 centimeter. Find the difference in pressure between the two sections of hose. Okay, I'm just going to ignore this answer here. I'm going to just go ahead and work on that. So let's see. Start out knowing that we have a hose that starts out with a radius r of 2 centimeters, and then somewhere that narrows down to a radius of r of 1 centimeter. R is 1 centimeter. And we know that the volumetric flow rate is 1 liter per second. Okay, so we know that that volumetric flow rate is maintained from here to here. So what changes? Well, we know the volume is equal to the area times the velocity, which is equal to area 2 times velocity 2. So we know since this is a smaller area, we're going to get a larger velocity out of that section. So the velocity vector will be larger here than it is here. And we know this area, since this A1 is bigger than A2, and therefore V2 is bigger than V1. All right, so I can't remember. Oh, the problem was asking what's the pressure difference. You can see we can't get pressures from here, but we do know that since this velocity is higher, the dynamic pressure the static pressure is going to be lower because it's given up its pressure, the static pressure pressing in all directions, to give the fluid a dynamic pressure in a single direction. So from the Bernoulli relationship, we know that the energy is conserved. This relationship is pressure 1 plus 1/2 the density, velocity 1 squared. There's a term involving the height, the vertical height, but it didn't change in this case, so we're going to leave that out. P2 plus 1/2 rho V2 squared, excuse me. So since we know that V2 is greater than V1, we know that P2 is actually, again, V2 is greater than V1, therefore P2 is less than P1. So V2 greater than V1, therefore P2, since these are constant, this is constant, this is larger, therefore this must be smaller. So P2 is less than P1. So I can, through this pressure difference, I'm going to say P1 minus P2 to get a positive value equals P1 minus 2 equals 1/2 rho V2 squared minus V1 squared. Okay, let's go ahead and, so here's our equation we're working with here. Let's go ahead and solve that. I'm going to need a little space here. So let's first figure out what V2 is. So the area, we know area is equal to pi r squared. So if I plug this in here, I know pi times 2 centimeters squared times V1 equals pi times 1 centimeter squared times V2. So you notice the pi drops out, and we get that V1 4 times V1 centimeters squared. Oh, the centimeters squared drop out as well. Equals V2. So we know V2 is 4 times V1. And that's going to help us in this relationship right here. Okay, I've been so sloppy, I need some space to do the calculations now. So I think I'm going to go ahead and just clear this. We know 4 times V1 equals V2, and we know that P1 minus P2 equals 1/2 rho V2 squared minus V1 squared. So let's put some of these numbers in here. We know 1/2 rho 4 V1 squared minus V1 squared. I'm substituting V2 into this here. So we have 16 over 2 times rho. Oh, excuse me, I don't know where I got that 16. 16 minus 1 is going to equal 15. So 15 over 2 rho times V1 squared equals this distance, P1 minus P2. Okay, so we've got the difference. It's equal to 15 over 2, or 7.5 rho times V1 squared. So we sort of need to know what V1 squared is. So we know that 1 liter per second is our volumetric flow rate, is the area times V1. So the V1 equals 1 liter per second times 1 over pi 2 centimeters squared. So roughly V1 equals liter, which is 1,000 centimeters per second, times 1 over pi 4 centimeters squared. I just squared this term right here. So it's equal to about, this is a S, 250 over pi. This is centimeters cubed, excuse me, a liter is 1,000 centimeters cubed. So we have now in the units, this is centimeters per second. 250 over pi, that's about 3.14. So I'm just going to call that V1 is about equal to 80 centimeters per second. And I know the difference here is 7.5 rho V1 squared. So 7.5 times the density, which is 1 gram per centimeter cubed, times 80 centimeters per second squared. So it's equal to 7.5 times 80 squared times 6,400 grams per centimeter second. Now you can see I have a bit of a problem with the units here. 7.5, here's a number that I have to compute to. Roughly 8 times 6,000. I'm going to call that 56,000. 56,000 grams per centimeter second times 100 centimeters in a meter times 1 kilogram is 1,000 grams. So you can see that this cancels somewhat. We have 100,000, that leaves 10. Centimeters, grams. So we get 5,600 kilograms per meter second, which is equal to you can convince yourself that's a Newton per meter squared. So 5,600 newtons per meter squared is the difference in pressure.